By 2014, deep learning was dividing into two distinct tracks. Discriminative models, aided by backpropagation and dropout, were successfully classifying complex data at scale. But generative models, networks designed to create entirely new, realistic samples from scratch, were stalled. The barrier was a mathematical requirement. To train a generative model, engineers typically had to compute an explicit maximum likelihood to estimate the probability density of the data. In high-dimensional spaces like images, explicitly modeling that distribution required calculating partition functions. These probabilistic computations were highly intractable, bogging down the networks. The standard historical workaround was to use Markov chain Monte Carlo methods to sample from these complex distributions. But in deep networks, these chains struggled to mix effectively between different modes of data, resulting in blurry, imprecise outputs. Ian Goodfellow and his colleagues approached the problem from a different angle. They abandoned the attempt to calculate the explicit probability density function entirely. By utilizing a mathematical bypass, they traded those intractable probabilistic calculations for standard differential optimization, bringing generator modeling into the realm of pure backpropagation. Instead of framing generation as a statistical density estimation problem, they reframed it as a two-player adversarial game. The first player in this diagram is the generator, a multilayer perceptron that maps a random noise vector drawn from a simple prior into the actual data space. The second player is the discriminator. It is a separate multilayer perceptron that acts as a binary classifier. It receives an input and outputs a single scalar, the probability that the sample came from the real training data rather than from the generator. Goodfellow conceptualized this with a counterfeiter and police analogy. The generator is a team of counterfeiters producing fake currency, while the discriminator is the police trying to detect the fakes. They have perfectly opposing operational incentives. This competition forces both networks to improve. The police get better at spotting anomalies, which forces the counterfeiters to refine their methods until their output distribution mimics the real training data. Because both players are simply multilayer perceptrons, the system requires no complex sampling techniques. The entire architecture can be optimized simultaneously using standard backpropagation and dropout. This adversarial architecture turns the generation of sharp, sampleable distributions into a gradient descent problem. It eliminates the need for Markov chains or approximate inference during learning. This equation governs the GAN architecture, a two-player minimax value function. The discriminator maximizes this, evaluating near 1 for real data on the left and 0 for fake data on the right. The generator minimizes the right term, pushing evaluations of fakes toward 1. This setup dictates exactly how the networks learn. The discriminator receives gradient flow directly from the raw training examples, learning the features of the real data distribution. The generator, however, receives its parameter updates exclusively via the gradients flowing backward through the discriminator. The implication here is that the generator never directly observes a piece of real training data. This structural isolation prevents the generator from directly copying input components, as it must learn to satisfy the discriminator's feedback rather than replicating raw pixels. It provides a statistical advantage. The generator is forced to map the implicit data distribution purely by learning the conceptual boundaries that the discriminator establishes. The central theoretical question of the 2014 paper was whether this adversarial game actually converges to the true data distribution. The authors proved convergence through a formal sequence. First, Proposition 1 proves that for any fixed generator, there is a closed-form solution for the optimal discriminator, shown by this equation. This ratio compares true data density against generated density. By substituting this optimal discriminator back into the original value function, the math collapses to a simplified virtual criterion. This derives the Jensen-Shannon divergence, a symmetrical measurement of statistical distance between two distributions. The Jensen-Shannon divergence has an absolute mathematical bound. It is strictly non-negative, and it evaluates to exactly 0 if and only if the two distributions are perfectly identical. Because the generator is minimizing this function, the unique global optimum is reached at the exact moment the generated distribution equals the data distribution. At this equilibrium, the generator perfectly mimics reality. Consequently, the optimal discriminator is forced into a state of confusion, outputting a 50% probability for every input it receives. This anchors the theory. The adversarial game is a mathematically rigorous objective, where minimizing the value function minimizes the divergence between synthetic and real data. That proof relies on infinite capacity and a fully solved discriminator. Training finite multi-layer perceptrons on finite datasets introduces mechanical friction. Optimizing the discriminator to perfect completion at every single step is computationally prohibitive. On a finite dataset, it also triggers severe overfitting. Algorithm 1 solves this with an alternating stochastic gradient descent loop. Engineers use a step ratio to keep the network synchronized, typically one step of discriminator ascent followed by one step of generator descent. Synchronization is vital to avoid what the authors termed the Helvetica scenario, or mode collapse. If a generator trains too far ahead of a lagging discriminator, it collapses multiple latent noise vectors into a single identical output to trick the judge. There is also a flaw in the theoretical objective of minimizing the log probability of a correct rejection. Early in training, the generator is so bad that the discriminator rejects fakes with near 100% confidence. Look at this plot comparing the early stage gradients. When the discriminator is highly confident, the theoretical function on the left saturates. The slope flattens, the backpropagated gradient vanishes, and learning halts. Goodfellow's practical fix was an inversion. Rather than training the generator to minimize correct discriminator probabilities, the network is completely rewired to maximize the discriminator's mistakes. This non-saturating variant alters early training dynamics, providing a steep, powerful gradient when the generator needs it most, while preserving the exact theoretical fixed point. The formal guarantees of a GAN become practically executable only when implemented with this non-saturating loss, ensuring the gradient signal flows even when the generator is at its absolutely weakest. Bypassing the explicit calculation of likelihood created a new paradox. Because the model's distribution is only implicit, there is no direct way to calculate its score on a held-out test set. In this chart recreating Table 1 from the paper, you see the 2014 workaround. The engineers generated synthetic samples and fit a Gaussian Parson window to them, allowing them to estimate a test set log likelihood for datasets like MNIST and the Toronto Face database. The authors placed strict caveats on this evaluation method, noting its high variance and its weakness in high-dimensional spaces. Because of these mathematical limitations, visual inspection of the generated sample grids remained a necessary qualitative benchmark for success. Buried in the caption for those sample grids, specifically for Figure 2, was an architectural foreshadowing. For one of the image sets, the authors briefly deployed a convolutional discriminator paired with a transposed convolutional, or deconvolutional, generator. While relegated to a single caption in 2014, that specific variant provided the architectural template for the DC GAN standard, which later enabled the stable training of deep convolutional generators. By abandoning the comfort of explicit likelihood and embracing the instability of a non-saturating adversarial game, Goodfellow and his team successfully mapped a pure backpropagation pathway to generating complex, highly realistic data distributions.